My name's Dr. Mark-0Paul Buckingham, MP. I'm a mechanical engineer by background, and I'm Managing Director of Xi Engineering. So at Xi, we like to improve technology, and basically we like to make the world a better place using technology or removing technical barriers to technology deployment. So what we do is merge the real and virtual worlds. So we do a lot of measurement and we combine that with simulation in order to produce digital twins. I'll come to some examples of that. But our core software platform is COMSOL. I don't know if you guys are aware of it. They're actually just there waving at us. Thank you very much, guys. So COMSOL is a multiphysics platform. As you can see, we can look at electromagnetics, we can look at heat, we can look at acoustics, and we can do all of these simultaneously. So depending on the product or system, we can customize it. And what we love about COMSOL, opposed to so much of a black box, rubbish in, rubbish out risk that you run with simulation, we can lift the hood and we can see what code is running. And in certain situations where there isn't a code, we can actually build our own algorithms and put them in there. So, first of all, helping clients understand technical challenges through the multiphysics. I'll give you examples of different systems we've done. And as I said, removing barriers. Basically, if you want to get to market quicker, faster, reduce the time and save cost, I think everyone would be in agreement there. And you can do this with multiphysics simulation. So I'll come on to some examples. So virtual prototyping, I've got one here that I will talk about. This is an electrostatic speaker from Warwick Acoustics. I think they did initially have something to do with Warwick University. We work with these guys to reduce the time to market. We actually reduced the cost of the device and actually gave them a better product. So this was a study done by the Aberdeen group. It's a little bit out of date now, so I'm sure the figures are a lot better. But in terms of companies that are using simulation opposed to standard techniques for project development, where they're actually physical prototyping, testing, and going back around that cycle. So 9 times reduction in development time, 4 times reduction in product cost. Obviously, decrease warranties because you reduce risk, and you can test a lot more things in the virtual world. And then product introduction rates or delivering on time. Like I say, that's an old study by the Aberdeen group. There have been many more, but basically, if you're not simulating, you should really think about it. So, as I was describing there, I'm going to use these guys as an example. So, they had their concept. This is an electrostatic speaker. It has about 50 different variables to optimize. So you're looking at the mesh, you're looking at the mesh weave, you're looking at the mesh material, you're looking at the spacings, you're looking at the geometry, you're looking at the spaces, you're looking at the film, which is effectively a crisp packet, the thickness of the film, the coating of the film, the tension of the film, and on and on. And these guys were basically building a prototype, spending a week or 2 weeks to test it, then picking up the next variable and going back around this loop. So I can't use a pointer here, but prototype, 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 all pushing out the time to market. So we just said, stop. You don't need to do that. What we'll do is get a validated model and cut out many of those prototyping phases whilst being able to optimize all the different variables. So I'm going to be talking about digital twins. So a little bit of education about digital twins. I'll put this down. So it was Michael Greaves that first came up with this, nearly 20 years ago now, back in 2002, the concept of a digital twin. So the concept has been around a while. In speaking to some of you beforehand, the definition of digital twin is somewhat spurious still. So I looked for a few different examples of what people believe a digital twin is. So I'm sure you can all read. I'll let you just take those in. The middle one is Michael Greaves, by the way, who founded who first coined the phrase. So for me, a digital twin is combining the virtual world with the real world, taking real world data that can be either live or buffered, but as long as the two are tied together, for me, it's a true digital twin. But why is this happening now? Why are we all talking about digital twin? Why is it possible? Well, basically for me, it's down to 2 points. One is Moore's law. I'm sure you're all aware of that in terms of computing power growing. It was a great prediction or a self-fulfilling prophecy based on a few initial points, which we've done pretty well at, but fundamentally, large-scale computing power is here. We can use it, we can access it. And also, the Internet of Things or connectivity, so we can do the grunt mathematics, we can create multiphysics simulation or full-scale digital models that actually represent the real world and the complexities within it. So we can run those and we can connect it to the real world. So it's only fairly recently that these two have really come together, so we can have digital twins sort of everywhere. One example would be, we were simulating a digital twin of General Electric's wind turbine. It was the largest onshore wind turbine back in 2010, 240 meters high. We were looking at high frequency noise issues, so we had a full model of it. We measured the turbine, we calibrated it, validated it, and then propagated the noise 8 kilometers. And because of the frequency and the mesh size, this was a huge amount of computing power which we needed. And what we did, we actually took it to the UK Supercomputing Centre. It happens to be in Edinburgh where we're based, but it's kind of irrelevant. So we migrated our model so that it wouldn't take like 3 weeks to solve. But we no longer have to do that. We can just go on cloud computing and turn it up or down. So we really are at the point where computing power is accessible, it's easy, you can throw your models onto it, just depends how much you want to spend, and it's connected to the real world. So for any digital twin, or any virtual prototype or simulation, for me, validation is key. You've got to avoid rubbish in, rubbish out. So what we do at Xi is spend our time ensuring that we can take real world data and the model or the simulation will act exactly as it does in the real world. We will then go back to the model and trying to simplify it, look at different variables, take them out, because what we want is an efficient tool that gives us the information we need quickly and rapidly and is not computationally expensive, or so these things can solve, so you can run them again and again. It lets you understand your system better. One of the things we always not necessarily struggle with, but most people think they understand their products really well, but when you get down to certain levels, even a measurement campaign, you can only measure so many things. There are gaps in there. So building a true model that takes into account the different physics you want, you can fill in the gaps and understand why you're getting those readings. So it really helps understand the product. I'm hammering this home, but build less real-world prototypes. Do loads and loads of virtual ones in the same time as you do one or two. And it's a risk-free environment. What if we did this? What if we tried that? You've got decisions in the product development process, and quite often, the complicated stuff you'll shy away from or not necessarily push. But you can do this once you've got that base model that's calibrated against the real world, validated base model. You can test, any number of variables quickly and risk-free. So I'm just going to talk about some real-world live digital twins now. I don't know if you guys reckon, this is a terrible picture on the right here, I do apologise. So Ocado, the jingle gets stuck in my head, all there's Ocado just for you apparently, but that's the grocery side. They have the Ocado technology side. So Ocado are doing this amazing thing. They are optimizing 3-dimensional space for goods. So they have these robots, 2,000 odd robots running around the top of this grid. They miss each other by 8 millimeters, and they're harvesting boxes. So they're 21 high or 1 high or 7 high. It's just an amazing thing to watch. But we've created a digital twin of the actual grid because they want the design cycle start to finish for a new grid to be reduced by half. So to do this, they want to be able to optimize a design solution, test it, ensure that they know it can work for the 20-year lifespan, and not ridiculously over-engineer it, make sure it's fit for purpose, but get this design process quicker. So we've made this huge digital twin, 250 meters by 350 meters. We've put load sensors on the grid. We've had to get in and out of the bots. And now we've been able to validate that so we can start looking at different options and design options, and fundamentally getting the start to finish grid design life cycle down by half because we're adopting digital twins. So totally different scale. This is printing for diagnostics in medicines. So this is a company called Arrayjet, and what they do effectively, they've adapted a printer head to actually print samples for scientific testing in laboratories, so they can do multiple small little pipettes and then take that through the lab process, so they speed up the lab process. So we've done a lot of optimization with the gaskets, with the microfluidics in this one. So looking at microfluidics, looking at the structure, looking at the gasket seals, because they'd been having a few sort of, why is this happening, why is that happening? And again, using a digital twin to help get an understanding of this, so now that we can crank that cycle. I've talked about these headphones. I didn't tell you how much they are. I did avoid that. So this company got in touch with us, and they were trying to hit a market that is £10,000 to £30,000 for a pair of headphones, which I wasn't aware existed until they made the call. But apparently this is, well, there's two real players in this: sound professionals, so people that listen to sound as a job. So if you wanted to set up a room at home, it's going to cost you about 100 grand, or you could get a pair of headphones for 10 to 30. You know, there's obviously a cost saving there. But what they needed was really fat sound reproduction. So effectively it's the same as you would have heard it. We've got a pair of these headphones actually on our stand. We're just around the corner. What stand number, George? J46. Thanks very much. And so we optimized all these 50 odd variables. We ran a couple of computers. They launched this in Las Vegas in the January in the tech show. They'd never put a product on the market before. This product, they managed to get it in at 5 grand, so half the bottom end of that marketplace. And they took all the awards. So this pair of headphones has got something like 14 awards from everyone in the industry. And having never launched a product before, you know, for me, this is a prime example of using a digital twin to optimize the design process, reduce it, and get to market ahead of other people. Their ultimate market is actually automotive. This thing weighs, with the casing, weighs about 26 grams. Without the casing, it's about an 8 gram driver. So you've got 8 to 10 speakers in your car. So you can turn that into grams, so obviously efficiency saving and so on, but really good high quality sound reproduction within a vehicle. So we designed this one. We then went on to their high end one, which is an eye-watering £25,000, which we did improve it. You know, people are like, is it worth 20 grand more? Basically, I've tested headphones now, and once you get past £1,000, that's, you know, I don't think I'm a sound professional at all, but they're good. But now we're putting these in cars, in headrests, in the top, and again, we can simulate this within the virtual space, calibrate against real-world data, and make that production cycle or get to market quicker. So here's a mesh of one of the wind turbines. We've actually modelled most of the wind turbines around the world off the big players, but for them, the cost to develop a solution and actually prototype it or change it, you know, is huge. These machines cost roughly £1 million a megawatt. This device was a 2.5 megawatt. Your current onshore wind turbines now are about 5 megawatts. So you've got a £5 million machine. So instead of going through that long and complicated development process, we'll go and measure it, get a calibrated model, and from there do the what ifs. You know, what if we did this to it? What if we did that to it? And then we'll build the final prototype. You know, all's good, and off you go. So we've reduced a lot of acoustic emissions and seismic emissions for wind turbines across the globe. Anyone seen a tidal turbine before? You won't have heard about this one probably. A few have had quite a few failures. This one didn't. We were there from design of this concept right the way through. They were looking at a 5-year maintenance-free period, because basically tidal turbines are great because you know when you're going to get energy into them. The downside is you've only got a 45-minute window to actually access it in between high tides, which is quite challenging. So you don't want to do that very often. So we did a holistic model of the overall system. We optimized the bed plate design. They were taking lots of different subcomponents from suppliers. They'd never built one of these before as well. So in this case, we had to use data from alternative or adjacent industries, like our work with the wind turbine manufacturers on their gearbox, their drive systems. Eventually we took it through the prototyping, and again we can verify the model, and from there we help them design and deliver this. So it's a 1 megawatt system that's been up and running in Orkney in Scotland now for 5 or so years. Anyone heard of Magway? Brilliant company, really, really exciting. So Hyperloop, you've all heard of Hyperloop? Yeah, so putting people in a vacuum and throwing them down a tube. So Magway thought that Hyperloop's pretty cool, but there is a risk involved in putting people in a vacuum. So they were like, well, why are we sending people? Why don't we just send goods? To get, the biggest growth in UK traffic, road traffic, over the last decade has been the white van man. Basically, Amazon, everyone else delivering. A decade ago, you'd see one van down your road. Today, there'll be 20, 30 coming down, depending where you live. So that's a lot of carbon emissions. That's a lot of transportation logistics. So they've taken what is a standard infrastructure pipe at 900 mil, 90 centimeters, and they've developed an electric drive system. So they have totes. So this thing here, basically totes are the same as what Ocado use. They're a grocery box. They're not standard. Brilliantly, the industry's managed to do that, but they are roughly the same. So whether it comes from Ocado, Virgin, Amazon or others. So what they've done is develop this linear electric motors, and they can run these things super fast and behind each other. They are just now, so we've been helping them optimize the subframe structure, the electromagnetics, and the actual motor and drives. So for them, it's not so much at the moment about optimizing for cost, but actually ensuring that this system is going to be maintenance free. So that's been their focus. So we are helping them. We built a digital twin of this, and these guys are taking digital twin to its full extreme. So not only do you have a physics-based model to enable the design and the product development, but they've got a client-based digital twin that can report on rates, supply, where all the systems are. Then they've got a maintenance-based digital twin as well. So we've been part of this architecture to basically build this whole system and network with real-time data and product development. So if you've not, go and check out Magway. It's a brilliant product. And they're going to do a lot of good fun stuff. We can't go anywhere without looking at electric vehicles. Batteries are big. They have been for a while. I'm sure plenty of you have been involved. This is another of our clients, Ilika, which is actually a solid-state battery. So for them, we're trying to optimize the actual mix that they're using to create the batteries. So again, they're going through this prototyping stage, but it's quite difficult to get into such small detail and understand. It's like baking a cake. They know what ingredients go in, and they do it. They don't necessarily know how those ingredients have mixed. And through a combination of measurement and building a now validated digital twin of the battery, we're looking at how we can then go back and actually look at the different ingredients for the cake in order to get better output from all of these batteries. Create some nice little models of what looks like lanterns, but these are the different molecules within the structure. So digital twin, it's a tool to understand your product or system. Like, if you've got lots of variables, it lets you just go and test them and do the what ifs and validate them. We've got the optimization capability. So what we do is we can do topology optimization against different variables. So we can set the computer running and go and do your thing. We do something crazy, and we use like human brains as well, and we do our optimization bit. And at the moment, it seems to be a merge of two. But certainly, what you can learn from setting computers off is quite phenomenal. Obviously, manufacturing techniques now are allowing us to build much different structures, and there have been quite a few presentations on that. But fundamentally, what you can do with a digital twin through product development is cut out the number of prototypes, get to market faster, get there with a better product. And these guys, Warwick, there's a quote on our stand from the CEO saying, we got to market faster and cheaper than we expected with a product that smashed the market. So utilising these tools through this, through your product development process is, for me, absolutely paramount, because everyone else will be doing it. So if you're not, you're going to be left behind. So I don't know if you know, but Toy Story was the first fully computer-generated feature-length film, and Sheriff Woody's speaking to the toys as they're actually moving house. But basically, he doesn't want toys to be left behind. So if you guys don't have a digital twin, as Woody would have said, get one.